My homemade jet engine needs more air. In the last video, we saw the engine spit massive flames out of the exhaust because it didn't have enough pressure or air to combust fully. So over the last 2 weeks, I designed and built the best 3D printed compressor I have ever made. The compressor is made out of 4 main parts: the impeller, the upper and lower volute halves, and the bearing well, which the bearings press fit into. Our assembly is held together using embedded hex nuts and brass heat inserts, making assembly and disassembly pretty easy. The drive assembly is made out of 2 parts, the motor mount and the tensioner arm, which clamp onto the bearing well using embedded nuts and screws once again. I had to turn my own drive shaft because I ordered the wrong size pulleys. The internal bore was 5mm, whereas my rod was 8. The drive shaft is keyed to the impeller to hold it all nice and tight, and there is a spacer to keep it from rubbing with the bottom of the volute. The rest is pretty straightforward. I'll let you guys piece it together. Upon assembling everything, I realized that a single 24-volt motor was not strong enough to power our compressor. I kind of expected this, and so I already had a double motor mount in mind. I just had to print it and then reassemble the motor assembly. The double motor setup still used the same 3:1 pulley ratio, but now had enough power to actually make some pressure. I tested our 2 compressors head-to-head in a static pressure test to see their maximum capacity, and found that our new compressor outperforms the old one by a factor of 3. We were producing 0.5 psi to the old 0.17 psi at an equal 20,000 RPM. Now, I was expecting our new compressor to be spinning quite a bit faster, so I did some more testing. The new compressor immediately made a massive difference, doubling our peak thrust from the last test, while only running at 17,000 RPM. The exhaust also had a noticeably smaller flame, indicating that we were combusting our fuel much more completely than before, even when I was dumping liquid propane. It was also glaringly obvious that our 3:1 drive ratio was putting way too much load on the motors, because they're rated for spinning at 20,000 RPM, and we only hit 17. So the logical solution was to replace our 20-tooth gear with a 40-tooth gear, resulting in a 3:2 drive ratio, which should allow us to comfortably hit 30,000 RPM. Following that, the next logical step was to let the compressor fall off my workbench, shattering the entire volute because I hadn't already rebuilt this thing enough times.
Ladies and gentlemen, I present to you the most cursed, bloody project I have ever worked on in my life.
Over the course of this project, I've run into camera issues, blown up power supply modules, had to rebuild glow plugs, had to rebuild multiple parts multiple times on this thing, and ran out of gas while testing. I was supposed to be done recording on Monday. It is now Friday. This build really does feel cursed.
Let's test this thing and move on before something else breaks.
A new static test confirmed our 30,000 RPM prediction and revealed to us the full potential of my newest baby. She clocked in at a maximum pressure of 0.76 psi at 31,000 RPM, a full 4.5 times more pressure than our old compressor made, and 11,000 RPM faster. Following this, I ran the same test we ran in the last video, where we compared performance at different nozzle sizes, and boy did we set some new records this time. Our best test produced 2.5 times more thrust than our most successful run in the last video. We took our peak thrust from 182 grams to 449 grams, which is just a hair shy of a pound. Our engine is making a pound of thrust. Anyways, this is that run.
This is the 38mm nozzle. Liquid propane.
The graphs for these tests turned out essentially how I expected them to. Similar shape to the last ones, but shifted back on the diameter axis because the compressor can handle higher pressure. The liquid propane thrust curve is where things start getting a little funky. The peak performance is shifted higher on the diameter axis, and I'm not fully sure why. Maybe the extra fuel ups the chamber pressure too much at lower diameters, choking the engine. For example, the peak pressure on the 29mm nozzle was like 0.72 psi, which is just short of what our static test showed is our new compressor's maximum pressure. So maybe it makes sense that at lower diameters the combustion is producing so much pressure that it really does choke the compressor. Next video we're going to work on liquid fuel injection and the use of kerosene. I'll see you guys then.